area now known as Cape Kennedy presented a landscape of sand dotted by palmettos. And then the missile age began, and test stands were erected. Missiles and their related equipment began to crowd the native landscape. Early successes and failures and their lessons made it clear that a new era was beginning. Ballistic missiles soon were modified and adapted for use as booster vehicles to open the way for the age of space. Modifications were slow, cumbersome, and expensive, but for their time, they did the job. Ultimately, standardized launch vehicles were developed, utilizing existing ballistic missiles as the foundation. As requirements grew more complex, so did the systems. In 1961, at the request of the President, representatives of the Department of Defense, the Air Force, and NASA reviewed all existing systems and those on the drawing boards. They concluded that nothing currently planned would meet projected needs. To satisfy military requirements, a system would need to have an instantaneous reaction time, maximum flexibility, and the capability of a maximum launch rate. The Air Force answer, Titan III, a space launch system designed to serve a myriad of needs in space, for today and tomorrow. To design this new launch vehicle, the Air Force contractor team began with a basic liquid-fueled core vehicle with a first stage, a second stage, and an upper stage known as a trans stage. In this basic configuration, the vehicle is known as the Titan IIIA. With solid propellant boosters added to the core vehicle, the configuration is known as the Titan IIIC. For certain specialized Air Force requirements, standardized components can be so arranged as to provide still other Titan III configurations. The Titan III itself is a new concept. Its launch facilities are also new. The once uncrowded Cape Kennedy landscape could not accommodate the new launch facilities, and 6.5 million cubic yards of sand were dredged from the Banana River to make way for the Titan III. This is Cape Kennedy today, as the pilot of a C-133 views it as he brings in the first stage of a Titan III from its manufacturer in Denver, Colorado. The Titan III's new home has been dubbed the ITL, the initial standing for Integrate, Transfer, Launch, the functions performed in this newly created area. The prominent structures are the Solid Motors checkout buildings, the Vertical Integration Building, where the core vehicle is erected and checked out, the Solid Motor Assembly Building, where the solid motors are built up and attached to the core vehicle, and the two launch pads, pads 40 and 41. A few facts about the ITL. It provides a number of advantages: quick reaction time, booster configuration flexibility, capability of accommodating a variety of payloads. In principle, the ITL is similar to an industrial assembly line, with the end product, the assembled Titan III, delivered at the end of the line, the launch pad, ready for launching. The Titan III's first stage, because of its dimensions, is the most difficult to unload. Titan III, though a new system, represents a proud heritage. As its name indicates, it is the third generation of the United States Air Force family of missiles and space boosters, the outgrowth of technology in both the liquid and solid propellant ballistic missile programs. It has been called a common carrier for space, standardized to deliver a wide variety of payloads, manned or unmanned, for their missions in space. While the aircraft makes the return trip to Denver to pick up the second and trans stages, The first stage is delivered to the Vertical Integration Building, VIB, for receiving, inspection, erection, and checkout. Because of aircrew rest time, there is usually 1 day between the arrivals of the first stage and the other 2 stages. Unloading of these smaller stages is relatively easy. Their first destination, too, is the Vertical Integration Building. The solid motors for the Titan 3C arrive by rail from the manufacturer in Sunnyvale, California. Each motor consists of 5 solid segments: an aft closure and thrust chamber, a prospector control tank, a forward closure dome, and the structure required for attachment to the core vehicle. They are first checked out at the Segment Receipt and Assembly Building and then moved to the Solid Motor Assembly Building, SMAB. With all stages on hand, follow the assembly line through to the desired end product. After initial checkout, the first stage is hoisted into position by an overhead crane. It is raised and moved to one of 4 bays and placed on a launch platform. The statistics are impressive. 71 feet high, 10 feet in diameter. Its weight, empty, is only 13,000 pounds. Fueled, it weighs 268,000 pounds. Its thrust, 470,000 pounds. Burning duration, 146 seconds. The VIB itself boasts some noteworthy statistics, as tall as a 23-story office building and closing 9 million cubic feet. Following securing of the first stage, the second stage is erected in the same manner. 37 feet high and 10 feet in diameter, this stage weighs 5,500 pounds empty and 74,000 pounds fully fueled. Engine thrust, 100,000 pounds. The burn duration is 206 seconds. Basically, the first and second stages represent a Titan II vehicle. With the second stage in place, the trans stage is erected. The trans stage, or space switch engine, as it is sometimes termed, is the key to Titan III's versatility. It is designed to provide the capability for multiple restarts, for changing orbit in space, and to achieve lunar or deep space trajectories. Its engines develop a total thrust of 16,000 pounds and a burning time of more than 7 minutes. 10 feet in diameter, 15 feet high, the trans stage weighs 4,000 pounds empty and 28,000 pounds fueled. In all 3 stages, storable hypergolic fuels are used, eliminating the need for ignition systems and simplifying ignition at high altitudes. The basic core vehicle is now assembled. A long checklist on every system and component must be accomplished before it is certified as ready for launch. In the high bay area of the VIB, 4 Titan III vehicles can be assembled simultaneously, their payloads mated to the vehicle and all systems checked out. Checks completed, the core vehicle is ready to move. As it leaves the VIB, the 3-stage Titan could go directly to the pad for launch as an A configuration Titan III. In this case, however, it will move to the Solid Motor Assembly Building to be fitted with 2 assembled solid motors. 2 Aerospace Ground Equipment Bands, AGE, are connected through special ducting to the transporter which moves the core vehicle from the building. The AGE is required for checkout and launch. The van's electrical and mechanical equipment remains connected to the booster from assembly until launch. 2 800-horsepower locomotives move the vehicle. These engines, Korean War veterans, were refitted for their Titan III duty. They operate over the 19 miles of ITL tracks at speeds between 1/4 of a mile and 5 miles an hour. In the SMAB, contractor crews lift the motors into position with an overhead bridge crane and a special lifting sling. They are mated to the core vehicle on the transporter. Each of the solid motors is 85 feet high, including the nose fairing, and 10 feet in diameter, and each weighs more than 500,000 pounds. Total thrust of the combined solid motors, 2.4 million pounds. Now, the final step, the end of the production line, the launch. At the pad, the Titan III-C could be launched immediately or held indefinitely. Titan III has a built-in ability to react rapidly to mission changes. This is what it's all about: the payload, the payoff. In this case, the payload consists of 8 communication satellites, which the Titan III-C will place into position as part of a military communication satellite band around the Earth's equator in an approximately 20,000-mile-high orbit. As the launch date nears, all systems are double-checked. The capabilities of the Titan III-C are varied. For a 1,725 statute-mile circular orbit, payload capability is 15,400 pounds. For a 115 by 1,725-mile elliptical orbit, the payload capability is 20,000 pounds. Titan III-C can also boost 5,000 pounds for a lunar mission. In the data transmission room of the VIB, personnel check and calibrate the banks of electronic computers and recorders, ready to receive the telemetry information during flight to provide in-flight and post-flight analysis. Launch day. All loose and unnecessary items are removed from the pad. Each function from this point on is done by checklist and time schedule directed from the Launch Control Center. Located in the VIB 3 miles from the pad, the Launch Control Center is the nerve center of the ITL. This room, with no exterior windows, replaces the old familiar reinforced concrete blockhouse. 14 TV cameras scanning all areas of the pad serve as the eyes of the control center. Here, Air Force contractor teams bring months of preparations to a climax. With the expected blast of smoke and flame, the Titan III-C lifts off. This is but one launch of many. By its record to date, Titan III has proved that it has fulfilled its design objectives. It is standardized, it is flexible, and more, it is reliable. It is serving now and will continue to serve in the future as the much-needed vehicle for payloads designed as part of an overall program to ensure that in space, America is never second-rate. Only a few years ago, the area now known as Cape Kennedy presented a landscape of sand dotted by palmettos. And then the missile age began, and test stands were erected. Missiles and their related equipment began to crowd the native landscape. Early successes and failures and their lessons made it clear that a new era was beginning. Ballistic missiles soon were modified and adapted for use as booster vehicles. As requirements grew more complex, so did the systems. In 1961, at the request of the President, representatives of the Department of Defense, the Air Force, and NASA reviewed all existing systems and those on the drawing boards. They concluded that nothing currently planned would meet projected needs. To satisfy military requirements, vehicles, to open the way for the age of space. Modifications were slow, cumbersome, and expensive, but for their time, they did the job. Ultimately, standardized launch vehicles were developed, utilizing existing ballistic missiles as the foundation.